So we're going to look at these half-life problems. So here it asks, how long will it take for 25% of the original sample of radon-222 to remain? So my starting point on these problems is always going to end up being the whole amount. So if it's percent, it's going to be 100%. If it's a fraction, I'm going to start with 1. If it gives me an activity level, whatever that starting activity level is my starting point. So since this is a percent one, I'm going to start with 100% is everything. After one half-life, 50% of it remains. After another half-life, I chop 50 in half and I get to 25. Notice I don't go 50 down to 0. I take 50, chop it in half, and I get to 25. Each arrow here represents a half-life. So this is 3.28 days from my table that's given up here. You will always be given the table. You don't have to memorize half-lives of different isotopes. The shorter the half-life, the more active it is, and so the more radioactivity you would be exposed to with it in a short term. So 3.28 plus 3.28 is going to be 6.56 days. So how long is going to be 6.56 days? So that's how I'm going to do that first one there. Next one asks about hydrogen-3. How long will it take for 6.25% to remain? So I start with 100% because, again, it's giving it to me in percent. After one half-life, it's 50. After another, it's 25. After another, it's 12.5. After another, it's 6.25. Each half-life, I have 1, 2, 3, 4 half-lives. So after 4 half-lives, I'll have 6.25%. 4 times the half-life for hydrogen-3, I look for my table, is 12.3. So I'm going to take 12.3 times 4, and I'm going to get 49.2. The unit it gives me is years, so 49.2 years. So that's how I would do that second one. Third one says, given a sample of atoms and 1/32 of the original radioactive atoms remains. So it's giving me a fraction. So my starting point in this case is going to be the number 1. So I'm going to start with 1, and after one half-life, I have a half of it remains. Then a half of a half is a fourth. Half of a fourth is an eighth. Half of an eighth is a 16th. Half of a 16th is a 32nd. So I go and I lay it out, and then I count how many half-lives. And I have 1, 2, 3, 4, 5 half-lives. 5 half-lives. Now, it says, though, this took 2,000 days. We know half-life doesn't change. So I'm going to know, I know 2,000 days equals 5 half-lives, or I could say 5x. So when I divide that out, I'm going to get x is going to be 400 days. So each half-life here would be 400 days. And when I do 400 days 5 times, I get 2,000. So again, same process, but since they give me the total time, now I can go backwards and figure out the half-life based on the information given. The fourth one is based on the activity. So based on the activity, I have 32 becquerels, and I'm going to end with 1. So I'm going to start with 32, and I'm going to decay until 1. So 32, 16, 8, 4, 2, 1. So that's the process I do to get to the 1 becquerel. Radon-222 is 3.28 days, and I have 1, 2, 3, 4, 5 half-lives. So 3.28 times 5 is going to give me 16.4 days would be the time that it takes. I would encourage you to pause the video now and try these last few on your own, and then go ahead and then check your answers. So I would encourage you, again, pause the video at this point, try the next 2, and then there's other practice problems for you to do later, but I would encourage you to do that. I'm going to now continue going through 5 and 6. So activity of becquerel is 25 and becquerels. And what will be the activity after 49.2 years? Oh, 49.2 years. So I need to figure out how many half-lives this is. So 49.2 years equals how many half-lives if each half-life is 12.3 years. So when I do that, I'm going to figure out that this is 4 half-lives. So after 4 half-lives, 25 goes to 12.5, that's 1. 6.25 is 2. 3.125 is 3. And then I do 3.125, and at some point if you want to round that, it's just fine. But I'm going to get 1.5625. So my activity would be 1.5625, and the unit on it is a BQ, a becquerel. Don't worry about, like, I don't know what a becquerel is. It's just the measure for the activity of it. But again, it starts at 25. I had to figure decaying 4 times, so decayed 1, 2, 3, and then that 4th time is that 1.5625. The unit on it would be becquerels. The last one, if I have 1 mole, oh, I'm sure you're excited, chemistry memories. If you have 1 mole of potassium 40, how many radioactive moles will remain after 2.56 times 10 to the 9th years? You might be like, oh my gosh, how do I deal with this crazy number? Look at the half-life for potassium 40 and can take 2.56 times 10 to the 9th is the half-life, which is 1.28 times 10 to the 9th times x. So when I divide 2.56, sorry, this should be 56, 2.56, and I divide that by 1.28, I should, and again, those are billion years, I'm going to get 2 half-lives. So then I'm going to decay 1 mole to a half mole to a quarter mole. So I end up with a quarter mole of remains after 2.56 billion years. So that's how you go about solving these half-life problems. I would encourage you to go to the end of your notes packet for further practice on these, because half-life is definitely something you'll need to know for the AP test and for your upcoming summative. Page 30 has more practice, and there will be a video with those practice on it too.